All right, we're at section 16.9, the Doppler effect. And I'm going to start here. Obviously, this isn't the PowerPoint. It's just a little demonstration from the physicsaviary.com. And it's called the Doppler Lab. And I'm just going to start it. And you can see this, it looks like a plane or something moving. And you can see, let me pause it. You can see that if we're an observer, let's just say right here, as these wave fronts meet us, you can see that they're compressed. So we'll assume we're right there, and we're getting these wave fronts coming at us pretty rapidly, and then as the source passes us, you can see that the wave fronts are much more spaced. That's essentially the Doppler effect. We've all experienced it. The you don't, it doesn't have to be a car horn or anything like that. Even a car, as it's approaching, you hear the yeah, as it passes you, it decreases in frequency. So they demonstrate these waves. You can see in all of these three, the waves are coming at you. They say the waves hit you at, one every 3 seconds. Well, when you're an anchor, you're going to get those waves one every 3 seconds. In all frames, the waves travel to the left, and their source is far to the right of the bolt out of the frame of the figure. So if you're stationary, anchored, you can see there's the anchor line there. You're getting this at a wave every 3 seconds. Well, if you're in B, I don't think there is a, oops, let's see. Let's stop that. If you're in B, no, yeah, it's, there's no more explanation. If you're in B, if the waves are still coming at you at one every 3 seconds, and you're traveling in this, you're getting, those waves are going to hit you much sooner. They're going to be less than one every 3 seconds. Now, if you turn the boat around and you're going with the waves, they're gonna take more. It's going to take more time to. They're going to be greater than 3 seconds, and so that's kind of the concept of the Doppler effect. So as you the S is the source. It's here a horn, and here's a bicycle rider. The bicycle rider is going at a velocity. This is the velocity of the observer. Apparently, there is no velocity of the vehicle of the source. So the change in frequency F prime. There is a frequency F. The F prime is equal to the velocity prime divided by lambda, which is lambda is the wavelength. That's the length between these wavefronts. And that's equal to the velocity plus the velocity of the observer divided by the wavelength. Okay, so F prime is equal to the velocity, and they're talking about the velocity of sound in air plus the velocity of the observer divided by the velocity of the sound in air times the frequency, the natural frequency, the observer moving toward the source. Now if the observer is moving away from the source, then it's a minus V0 divided by V times F. Now here's a lambda, the wavelength is equal to lambda minus delta lambda is equal to lambda minus the velocity of the source divided by the frequency. So here's the source, a point source is moving to the right with speed Vs. So instead of in the previous example, we had the observer moving. Now we have the source moving. You can see the observer A is going to hear a higher frequency. Observer B is going to hear a lower frequency. So here the source moving to the observer, that's this one. So the frequency is equal to the velocity divided by the lambda prime, and lambda prime is equal to lambda minus V source minus divided by F. So V over lambda minus Vs over F. So that's equal to the velocity divided by the velocity minus F minus the velocity of the source divided by F. So F prime is equal to the velocity divided by the velocity minus the velocity of the source times F. That's the source moving toward the observer. And the source moving away from the observer, that's observer B. F prime is equal to the velocity of sound divided by velocity plus the velocity of the source times F. Now, you can combine both of those into just one equation. F prime is equal to the velocity of sound plus the velocity of the observer divided by the velocity of sound minus velocity of the source times the original frequency. And there you can, I mean, if only one of them is moving, if the observer is moving and the source is stationary, then Vs is equal to 0. If the source is moving and the observer is stationary, then VO is equal to 0. Okay, so consider the detectors of water waves at 3 locations, A, B, and C in the figure. Which of the following statements is true? The wave speed is highest at location A. The wave speed is highest at location C. And the detected wavelength is largest at location B. The detected wavelength is largest at location C. The detected frequency is highest at location C. The detected frequency is highest at location A, and it's the E. The detected frequency is highest at the location C because you can see that they're compressed. They're compressed here. And so the detected frequency is highest at location C. And let's see. You stand on a platform at a train station and listen to the approach, and listen to a train approaching the station at a constant velocity. While the train approaches, but before it arrives, what do you hear? The intensity and the frequency of the sound both increasing, the intensity and frequency of the sound both decreasing, the intensity increasing and the frequency decreasing, the intensity decreasing and the frequency increasing, the intensity increasing and the frequency remaining the same, the intensity decreasing and the frequency remaining the same. The intensity increasing and the frequency remaining the same. In other words, that's as is approaching you, it's getting louder as it's approaching you, but the compressed frequencies that you're hearing are the same. So the intensity of the sound increases because the train's moving closer to you, but because the train moves at a constant velocity, it says there at a constant velocity, the Doppler shifted frequency remains fixed. So you're getting those compressed wave fronts approaching you. Now shock waves. Back when I was a kid, they didn't have rules about sonic booms, so we used to hear sonic booms all the time. And the sonic booms occur when the airplanes would go faster than the speed of sound. They were pretty common to hear. They have restrictions now of planes flying faster in residential areas, faster than the speed of sound in residential areas. So here they show you the envelope of the wavefronts forms a cone whose apex half angle is given by sine theta equals the velocity divided by the velocity of the source. And you get this, you get this cone of wavefronts. Notice the shock wave in the vicinity of the bullet. So sine theta is equal to Vt divided by the Vs, the velocity of the source, times t. Well, the t's cancel and you get V divided by Vs. And here's a shock wave shown in a boat because the the boat, let's see, the V-shaped wavefronts produced by a boat when the boat speed exceeds the speed of the surface water waves. Jet airplanes traveling at supersonic speeds produce shock waves. They're responsible for the loud sonic booms. You don't hear those much anymore, if at all. The shock wave carries a great deal of energy concentrated on the surface of the cone, with correspondingly great pressure variations. So the shock waves are unpleasant to hear and can cause damage to buildings when aircraft fly supersonically at low altitudes, and that's why they prohibit it. An airplane flying at supersonic speeds produces double boom because two shock waves form, one from the nose of the plane and one from the tail. You can sometimes see the air condensation from the when the airplanes are moving very, very rapidly. Okay, let's take a quick quiz. An airplane flying with a constant velocity moves from a cold air mass into a warm air mass. Does the Mach number increase, decrease, or stay the same? So the Mach number is the speed of the source divided by the speed of sound. Well, the Mach number decreases, and the Mach number is the ratio of the plane speed, which doesn't change, to the speed of sound, which is greater in the warm air than in the cold. Remember, the speed of sound is temperature dependent. So the denominator of this ratio increases, whereas the numerator stays constant. So if the numerator increases, the whole value decreases. So the Mach number decreases. And I think that's it for this chapter 16.